So here's what we've done so far. You observed that in this, you have 3 mesh currents. The mesh current in I1 is in the same direction that supplied 5 amps. So because of that, I1 is equals to 5 amps. They're in the same direction, so positive. When going through mesh current I2, we ended up with this expression. And here we saw that when we substitute I1 is equals to 5 amps, the expression reduced to this. So this part we have done. Now we want to do the same thing for mesh I3. Now for this mesh I3, what are we doing? When we start looping as well, you can start from any point. I can start from here. First, you find this one here. Now it's completely up to you here. I want to show you the treatment when you use the polarities already set and when you use just the standard way of doing it. If you use the way we approached it on mesh 1, we did not set polarity, take for example, for this 2 ohm resistor. Instead, we say that, okay, the resistance there is 4. We are looping as part of I3, so we'll say I3 will be positive. It is shared with I2, so we said minus I2. Then we continued, would have continued here and found that 8 ohm and said plus 8 ohm. 8 ohm is not shared with anything, so it will be I3 there. Then we continue, we find the 20 volt negative first, so say minus 20 is equals to 0. This is how we would have done it the way we approached mesh I2. Now, what if you took into account polarity? If you were to follow polarity here for this resistor, you would say you're finding negative first for the resistor. So you'd say minus 4. But now to determine which current is positive, you would need to see which current follows this definition of polarity. You'd have to observe that I2 now is the one specifying this polarity, that positive comes first, then negative is down. So I2 would be the positive one. I3 would be going opposite to that polarity, since the flow of I3 indicates that positive must have been here and negative must have been there. So since I3 is opposing this polarity, I3 will be the negative one. This is how it would have been for this one. Then for the 8 ohm there, since we haven't set polarity, we'll still go with 8I3. Then for the 20 volt source, we're still finding it minus first. So minus 20 is equals to 0. This is what we would have had if we had set up polarity. Now you should see that the two methods still yield the same answer. They still yield the same final equation. So you can set polarity in advance, or you can just follow the method we've been using. If you simplify this, when you distribute the minus 4, observe that you have minus 4I2, then you have plus 4I3, then you have plus 8I3, then the 20 goes to the right. It's the same conclusion that you end up with here. 4I3, oh, that's this one. Then minus 4I2, and that's this one. Then plus 8I3 is equals to 20. You see that you end up with the same expression, so you can set up polarity or you can go with that expression we're using. So I'll stick to this one down here. We'll try to simplify it since it looks like 4 goes through and this are like. So have 4 and 8, that is 12. Is equals to 20. We'll divide through by 4, giving us 3I3 minus I2 is equals to 5. We'll make I2 subject to the formula here. I2 becomes equal to, it goes to the right, the 5 comes to the left, rearrange, 3I3 minus 5. So we now have the expression for I2, and remember equation 1 also gave us the relationship between I2 and I3. So get this expression, and where there's I2, we'll substitute. So this becomes 7. Where there's I2, we're putting 3I3 minus 5, then minus 4I3 is equals to 50. Multiply 21I3 minus 35 minus 4I3 is equals to 50. 35 goes to the right, the 4 and the 21 will interact. So 1 is negative, so when we say 21 minus 4, we get 17. Is it 17?
Yes.
The 35 will add to the 50, giving us 85. So that I3 is equals to 85 over 17. So I hope you guys are going through what I'm doing to make sure that the quick math I'm doing sometimes. Pardon?
That's giving us 5.
Oh, this can divide?
Yeah.
Okay, so this gives us 5 arms. So now we have I3 as well. Earlier we had I1. So you can now use equation 2 to know what I2 is. I2, we saw that I2 would be given by 3I3 minus 5. So this is now 3 by 5 minus 5. This would be 15 minus 5, giving us 10 amps. So just like that, we have figured out what I2 is. So the question wanted us to find I1, I2, and I3. We have found the 3. The last thing that the question wanted us to find is V0, the voltage across the 4 ohm resistor. Now, here is how mesh analysis works. The logic of mesh analysis is that by finding these mesh currents, you can use them to find the current in any branch. Because mostly what we are actually interested in are not the mesh currents, but instead the branch currents. What is happening through the individual components. So that will require the branch currents. Here they want us to know the voltage V0 across the 4 ohm resistor. To find V0, we need to know the current passing through that resistor so that we multiply it with that resistor to get the voltage in accordance to Ohm's law. Now, there is a direct relationship between I0 and the mesh currents that are affecting it. So if this is our resistor, the 4 ohm resistor, polarity has been said to be positive on top and negative down here. Observe that mesh current I2 is going downwards through that resistor. So this is I2. Mesh current I3 is going upwards through that resistor. Polarity for this resistor here, according to that positive negative arrangement, it indicates that the actual branch current is pointing downwards. So if the branch current here is I0, to determine what I0 is, we can say that I2 is in the same direction with I0, so I2 will be positive. I3 is in the opposite direction, so you get I minus I3. So you can get it like this. If you're not comfortable with this approach, you can come to the bottom down here and use the current law there. Because for this one, you would say, according to the polarity, the current through this resistor enters that node. So if the current there is I0 again, so sum of currents there equating to 0, I0 enters, so positive. I3 also enters, the mesh current I3 enters, so it will also be positive, but I2 leaves that node. So it will be minus I2 is equals to 0. When you make I0 subject, you see that I2 will be positive, I3 will be negative, giving you this expression. So observe that this expression and that expression are one and the same. And since we know the mesh currents, finding I0 can then be straightforward. I0, which is the current through that 4-ohm resistor, we saw that it is I2. I2, we got 10 amps. That was our I2. So I have 10 amps minus I3. I3 was 5 amps, so I have minus 5. When you get the difference here, we get 5 amps as the current through that branch. Once you have the current through the branch, you can now get the actual voltage drop, or the voltage drop across that resistor, times 4. The current is 5 by 4 gives us the drop across that resistor as 20 volts. Okay, that's how you're supposed to work it out. Any questions there? Okay, so we have just seen an example where you were just deploying mesh analysis to determine the mesh currents, and eventually we used the mesh currents to determine what was happening in a particular branch. And with that, we managed to work out this problem. Now, the next thing that we're going to do is, what if you had a current source shared between two mesh currents? Well, that leads us into a super mesh, which is what we have here. This is a basic concept or a basic question to help us understand that idea. We still have something more complicated, not complicated, a little bit more involving in form of this question. It's still, just like the previous one, or just like what we're about to do, it has a current source shared between two mesh currents. And then, of course, the grand finale is going to be that AC problem. Hope we'll have enough time for everything. But firstly, let's look at this one here. What do they want us to do? In this question, they're saying use mesh analysis to calculate the value of Vx for the circuit in the figure below. So where is Vx? Vx is the voltage across that current source. Tricky. But let's see what we have to do. So if we're using mesh analysis, then we know we need to know the mesh currents. So let's begin. So the mesh currents there have been defined, I1 and I2. So how helpful are they going to be? So let's try to determine them first, since mesh analysis is all about determining the mesh currents. So when we loop through the first one, we quickly see a problem there. We quickly find a problem. What is going to be the voltage, or what is going to be the voltage there? Because we know in mesh analysis, we are looping, yes, but mainly we are summing voltages, Kirchhoff's voltage law. So what are we going to have through that point, Vx? That is going to be a little bit tricky. Well, we can try to see it. Since we're actually trying to know what the voltage there is. If we tried to loop across this, what we'd actually have is going to be minus 10 here, which is the voltage here. Then we'll have plus 5, I1. But for this one, since we don't know how to get the voltage there, we'd literally have to say plus Vx is equals to 0. This is what we'd end up having here. In the same way, if we tried to do it for the other part, notice that we'd have minus Vx, because now when looping, we're finding Vx negative first. I am looking at it not as a current source, but as the voltage source that current source is producing, as a voltage that the current source is producing. That is why I am not even talking about that 2 amps, I'm just talking about this Vx here. So I have minus Vx. Then when I continue, I have plus 2I2. When I continue, I have plus 4I2 as well, as the last one equals to 0. I end up having something like this. Well, I'll hold on to these two expressions. I might not even need both. I might just need one. Now, how do we work out a problem like this the normal way? So I'm going to put aside the fact that they want me to find Vx. So I'll put aside this Vx for now. I just want to look at it as a question on mesh analysis. Because I'm taking that approach because I quickly see one thing about this equation. In this equation, if I know I1, I can easily find Vx. Because from here, I see Vx will be equals to positive 10 minus 5I1. So if I can figure out what I1 is, then I'll know what Vx is. Additionally, if I wanted to go with this expression, then it means that I'll just change this a little bit. These are both functions of I2. They can add up. So plus 6I2 is equals to 0. So for this one, I see that if I can figure out what I2 is, then I'll be able to know what Vx is. I don't need to do both unless if I just want to compare my values. I just need one of them. So I'll stick to this one. If I can figure out what I1 is, then I can easily know what Vx is. So let's go ahead and try to determine what I1 is. Well, in a normal setup, we actually don't even dare to loop through a current source because what will be the voltage there? We don't know how to get it. It's not given. We don't know the resistance there for us to say it's resistance times current. So in such a case, where you have a current source shared between two mesh currents, we usually resort into dealing with a super mesh. In that case, we start properly this side. We find minus first, so have minus 10. We continue. We have a resistor there. It's not shared, so have plus 5I1. We continue, but then we find a line, a branch, which has a current source. We avoid looping through branches which have current sources. So we continue, we find the 2 ohm resistor. We still want to make a loop. So we'll skip that, but now just treat this as a super mesh. We find the 2 ohm resistor, we'll get it plus 2, but now we recognize that it's no longer part of I1. That 2 is part of I2. So say times I2. Then when we continue, we find the 4 ohm there, also part of mesh 2. So say plus 4I2. And see that that was the last one because we are going back to where we started from. So this is equals to 0. Let's go ahead and simplify this expression. So here we see that I2 here, these are like terms, that will be 6. So 10 goes to the right, becomes positive. We have 5I1 plus 6I2 is equals to 10. This is the expression that we have. Let's hold on to this as 1. Or we can say this was 1, and this was 2, and so that this is 3. So what do we do? Whenever we end up with a super mesh, we must always come back and include the branch we put aside. In this case, we did not take this route because of that 2 amp source. So now we need to bring it back. So how do we do that? Pick a node where that branch connects, either the node down or the node on top. In this case, regardless of the node you pick, you still end up with the same conclusion. In some cases, you'll find that picking one node might give you something a little bit more complicated. So you might favor picking one node than the other. A good example is this one. Here you see that you're going to have a current source between 2 mesh currents. So at one point, you will have to come back and include this branch. There are 2 nodes where the current source or the branch joins the rest of the super mesh, the down one and the top one. But you see that the top one, you'd have to consider what is passing through this, what is coming through that, what is happening here, what is happening there. You'd have so much to consider. So for a problem like this one, the upper node would not be ideal for analysis. The bottom one, however, seems to be more straightforward because in this line, you have this coming in. In this line, you have the mesh current coming in. In this line, you have the mesh current going away. So here it will be more straightforward in terms of how you analyze it. Let's go back to our basic problem. So we said you can pick either the top one or the bottom one, won't really matter. So pick the bottom one here. So when you look at the bottom one, the 2 amps enters the node. So I'm summing currents at the node and equating to 0 according to KCL. The 2 amps enters, so it will be positive. I2 as well enters, the mesh current I2 enters, so it will be positive. The mesh current I1, however, is leaving that node, so it will be minus, is equals to 0. We see that we get the second equation relating I1 and I2. We can make I1 subject here. No, now before I make I1 subject, I realize or recall that I chose to use this expression for Vx. And in this expression, what I need to know is I1. So I don't want to know both I1 and I2. All I want is to know I1. So I will not eliminate I1. I will eliminate I2. So I'll make I2 subject of the formula. I1 becomes positive there. 2 becomes negative. Then I'll get this and substitute it in my equation 3. So I'll have 5I1 plus 6 I1 minus 2 is equals to 10. So this is 5I1 plus 6I1 minus 12 is equals to 10. This is 11I1 is equals to 22 when the 12 crosses. Divide both sides by 11, you get I1 is equals to 2 amps. Now that we have I1, remember, according to what we came up with, it becomes easy to now know what Vx is. So now we have 10 minus 5 times 2. So this will be 10 minus 10. And according to this, the voltage drop across that current source is actually 0. Is that okay? Yeah.
Introduce the KCL.
KCL, I think I spent a bit of time trying to analyze that part, but we introduce KCL, or we end up using KCL every time when we use a super mesh. When a super mesh is utilized or used, you always end up skipping at least one branch. You must always include that branch. The branch here is the branch that contains the current source. So you must then deploy KCL at a node where that branch connects, either on top or down here. Let's do it for up here. So for the top point, you see that I1 enters that node. I2 is leaving that node, while the 2 amps itself is also leaving that node. So if you use KCL there, enters to be positive, that is I1, leaving to be negative, that's minus 2, minus I2 is equals to 0. So making I2 subject, you end up with I2 is equals to I1 minus 2, which is exactly what we ended up with in the previous case as well. Is that okay?
Yes.
Okay. So this is how you work out this problem. Any questions up to here? Okay, seems like we are fine. We can move on to this one. Now this seems to be more involving, but let's see how best we could have answered it. Now, as we go through this one, you clearly feel the difference. The previous one, which is this one, seemed to have been more straightforward. But look at that, it was only for 10 marks. The next one is going to be slightly more heavy, but again, 10 marks. This clearly shows that life is not fair. Just joking. Okay, so let's begin. For the circuit shown in the figure, use the mesh current method to find the branch currents IA, B, C, D, E in the circuit shown. Check your calculations by showing that the total power developed in the circuit equals the total power dissipated. So how do we do this? Well, first, we need to define the mesh currents. So observe, you are supposed to use the mesh current method to find the branch currents. A, B, C, D, E are branch currents. So we're supposed to define the mesh currents first. So we'll define the mesh currents. Here, I'll set this to be my I1. Here, I'll define mesh current I2. Here, I'll define mesh current I3. And finally here, I'll define mesh current I4. Once the mesh currents have been defined, we can even set up our success criteria or our relationship between the mesh currents and the branch currents in advance. Or we can find the mesh currents first and then bring back that relationship. In this case, let's come up with the relationship first. IA is the branch current through the 40 ohm resistor. So if I wanted to come up with the relationship between IA and the mesh currents, how do I do that? We, for simplicity, can use the same analysis I used, same direction, opposite direction, and so on. Or we can use KCL at a node where that IA is going. Which method is better? Where IA is going, the node, or just analysis which current is in the same direction, opposite direction?
The node.
The node. Okay, so if we analyze the node where IA is going, observe that mesh current I2 enters that node. Mesh current I1 leaves that node. So summing currents there, IA enters, so positive IA. I2 enters, so positive I2. Then I1 leaves, so negative I1 is equals to 0. This tells us that if we wanted to know the branch current IA, while we know the mesh currents 1 and 2, just subtract I1 minus I2. That's the first relationship. So this tells us how to get the branch current if we know the two mesh currents, I1 and I2. In the same way, we can come to, let's say we wanted to know IC. IC is here. IC is here. So I can pick that node this side. So for this one, I see that IE is coming to enter. No, not IE. I won't use IE. I'm using the mesh currents, remember? I4 comes to enter that node. IC leaves that node. While ID, not ID, remember, I'm only analyzing for one branch current. The other two must be mesh currents. IC leaves. I4 enters. While I3 also enters, because I3 is coming like this, so I3 will be entering that node. So based on that, I have I4 enters, positive, IC leaves, so minus IC, I3 enters, so plus I3 is equals to 0. So this tells me that IC is actually equal to IC was leaving, I4, okay, it's I4 enters, I3 leaves. I see this direction. Okay, so, sorry. Yeah, I was seeing why is it that it doesn't make sense. Along this line, we have the branch, which is IC, leaving. Along this line, we have IE, not IE, I4, enters. Then along this path, we have I3, leaving as well. So I4 enters, I3 leaves. This way, when we analyze it now correctly, I4 enters the node, so positive I4. IC leaves the node, so minus IC. I3 leaves the node, so minus I3 is equals to 0. When you make IC subject, IC is equal to I4 minus I3. That becomes the second one. How I knew that the previous one was wrong, I just looked at it to say, this is that 35 ohm resistor. IC is going this way. I4 is in the same direction, so I4 has to be positive. I3 is in the opposite direction, so it has to be negative. So the one in the same direction has to be the same sign, positive, positive. The one in the opposite direction has to be the negative one. So I knew they had to be subtracting. They're not supposed to be adding. That's how I knew I had to double check. So this becomes the relationship that gives us IC if we know I4 and I3. What are we left? We're left with IB and IB and ID, including I. So we have three more. We have an expression for A, an expression for C. We have B, D, and E left. Now, when I look at IB is here. Now, I am reluctant to pick a node like this one because I have to think about it a bit too much in terms of the branches which are there. So before I start confusing myself with so many branches, I go back to the basic. The basic, the same one I described at first. If you have a branch like this one, the resist or the current through the branch current itself has been defined to be this IB. All you need is to look at how the mesh currents interact with that branch. Observe that mesh current I4 will be going this way, in the same direction with IB. So already I know IB is in the same direction with I4. So I4 will be positive. But when I look at the I2 will be in the opposite direction to IB, meaning I2 will be negative minus I2. Observe that this is quicker. In the same way, I can try to determine the others. I have B, I have A, I need D. D is this side. D and E are very straightforward. ID is only affected by I3. So you should be able to see that ID is equal to I3. They are even in the same direction. By the same logic, even IE is related to I4. They are also in the same direction. Any questions up to this point?
Can you repeat on how we call IB?
IB. So for IB is here. All I did was I isolated that resistor where IB is passing. The branch current itself, the branch current is going this way. This is our IB. Then I showed the direction of each mesh that affects that resistor. That resistor is affected only by two mesh currents, I4 and I2. So when I look at I4 is looping clockwise. And as it passes through IB or through the 10 ohm resistor, it will be going to the left. So IB or I4 will be going to the left as it passes through that 10 ohm resistor. But I2, however, also looping clockwise, notice that as it passes through the 10 ohm resistor, I2 will be going to the right. Once you have this, taking IB to be the positive one. If you don't want to say taking it to be the positive one, you can still just say sum the currents in that branch. You still should be able to get the correct answer. But take the direction of IB, the branch current, to be the positive one. It now means that I4, which is in the same direction, will also be positive. I2, which is in the opposite direction, will be negative. Do you see how I came up with the equation?
Yes.
Okay, so with that done, we can now proceed to try to determine the mesh currents, because we've seen clearly that if we know the mesh currents, we can easily get the branch currents that they want us to get. Well, the one where you have a current source on the edges are the most straightforward one, because all you need to see here is that the current source is in the same direction with that mesh current. So I1 is actually the same as 30 amps. They are even in the same direction, so the I1 will be positive 30 amps. Knowing I1 makes our life easier. We proceed to the next thing. When we come to I2, for I2, we notice that when we start looping, when we reach this point, we'll find a situation where we can't take this route. Remember the super mesh concept. Because of that, when we reach that point, we'll bypass, meaning we have created a super mesh. We need to go back and add that branch where the one we have ignored or skipped. So that is the loop we are going to create. Had it been that maybe you had another current source here, it would have meant that if you have another current source here, when looping, you'd come this way, come this way. You can't take this route because of that current source. No problem. Would go up. Come this way, now go up. Can you pass here? Is it a current source or a voltage source? It's a voltage source. You can loop through. You go like that, come like this. Is this a current source or a voltage source? Voltage source. You can pass through. So this is the super mesh should end up creating. For this one, however, much more straightforward. When we start, let's say we start from here, or we can even start from here. We come this way, we find the 40 ohm resistor, so say 40 ohm. We're looping through it, part of IA, not IA, part of I2, mesh current 2, but it is shared with mesh current 1. We continue, we reach this one here, that's the 10 ohm resistor, so plus 10. We are looping as part of I2, but that resistor is shared with mesh I4. We continue, we skip the branch with a current source, we find the 35. We are looping as part of I3, but it is shared with I4. Then we find a current source, positive first, 150. That's the last element we encounter before we reach our point. So this has to be equals to 0. Distribute and substitute. I1 is 30, so we'll have 40. I2 Then where this I1 we put 30, we have 30 by 40, 4 and 3, that's 12. Then the 2 zeros. Then we have plus 10 I2 minus 10 I4 plus 35 I3 minus 35 I4 plus 150. The 150 and the 1200 can go to the right. I2, that's 50 I2. I3 shows up only once. I4 shows up twice, both are negatives, so you have minus 45 I4. Then we have the 1200 negative plus 150, we get 10 and 50. Becomes positive on the right. So this is what we end up having. 3 unknowns here, I2, I3, and I4. Now, whenever we deploy a super mesh, we must always include the branch we skipped. The branch we skipped is this one. So we now go to where this branch connects. Here, we'll take the bottom node here. It's more simpler to deal with. For that node, the current through this branch enters. So that current is 3IA. It enters that node. Then you have the mesh current I3 also entering. So we'll have plus I3. Then we have the mesh current I2 going this way. So we'll have minus I2. So with that, we have 3IA. Oh, we can leave it like this for now. But what is IA? Let's go back. Do we have what IA is? Since we're interested in knowing the mesh currents first, here we did see an expression for IA, or how IA relates to the mesh currents. So it's a good thing we got these first, so that once IA shows up, we can get rid of it immediately. So where there's I1, remember, I1 is 30, so it will be 3 by 30. Then minus 3I2 plus I3 minus I2. I2 in, yes?
The I1 to compute
This one here?
this.
Okay. So,
Already replaced it.
yes, we have.
So delete
Oh, yeah. Yeah, thanks for that. We have already replaced, so no need to keep it there. Yeah, thanks for that. Okay, so now this is what we have now. So this and this are like terms, they'll go to minus 4. So you now have 90 minus 4I2 plus I3 is equals to 0. So here we can even make I3 subject. I3 will be equal to 4I2 minus 90. Next, taking that super mesh, already dealt with this entire part. So no need for us to come and consider this part. The only thing that we now need to do is to loop through that top mesh, the one for I4. So the one for I4, we can start from somewhere here. clockwise, we find positive 15ID first. Then we continue, we find that 35 ohm. So say plus 35. We are looping as part of I4, but it is shared with I3. We continue, we find the 10 ohm, so we have plus 10. We are looping as part of I4, but we're sharing with I2. That's the last one, so equals to 0. We already know the expression for ID. ID is equals to I3. So from here, where there's ID, we'll put I3. We'll distribute that 35. Now we need to sort out the like terms. I3 will get minus 20. I4 and I4 will get positive 45. Then minus 10I2. 5 can go through. So we have minus 4. That should be 9. There should be 2. We now have 3 unknowns, I2, I3, I4. Even here we had 2 unknowns, same unknowns though. Here we have 3 unknowns again, reducing us to a simultaneous equation or systems of equations. So we have 3 equations we need to solve as a system. Okay, so we now have these expressions. When you look at this, would you want us to go all the way, or you are able to solve the system of equations now?
We can solve.
As in we solve together, or you can manage on your own?
So,
Okay. So here, to solve these, you can use any approach. Cramer's rule is a perfect candidate as well, but I like old school substitution if it works. Here, in equation 2, I even made I3 subject already, so I'll use I3, substitute it or eliminate it in my other expressions just like that. So in equation 1, when I substitute I3, I'll have 50 I2 plus 35, where there's I3, I'm putting 4I2 minus 90. Then I have minus 45 I4 is equals to 1050. I need to simplify now. Okay, so here we're going to have 50 and 140. This is 190. And then minus 45 I4. The 150 goes to the right. So what will be the sum? 150 and 1050.
$42.00.
Okay. So this becomes 4. We'll do the same thing to 3. We'll eliminate I3. So you have minus 4i3, what are we eliminating? We're eliminating i3, so i3 has showed up already. So where there's i3, we're putting 4i2 minus 90. So this will be then plus 9i4 minus 2i2. Now it's simplification. 4 and 4 is 16. Then minus, what is minus and minus will be plus. What is 4 by 90?
360.
They have 360. Then you have plus 9i4 minus 2i2. Like terms, i2 there gives us minus 18. Then plus 360 plus 9i4. When we rearrange this, we can rearrange, but seeing that we are only going to remember two expressions, I will choose to make one term here subject. I will make I4 subject. If I make I4 the subject of the formula here, it means that all the others must go to the right. The 18 becomes positive the other side. The 360 becomes negative, yes?
It's fine. Isn't it to say 9 is common?
Oh, yes. So now 9 divides through, it will be 2i2. What will be 9 into 36? Is it a 40? A 4 there?
It's 40.
So this can be our 5. We'll then get this expression for I4 and plug it where we have I4 there. Oh, sorry, not that. So we're eliminating I4 now. So you have 190 I2 minus 45, where there's I4, we're putting 2I2 minus 40 is equals to 4200. So this is now 190 I2 minus 90 I2, then plus, what is 45 by 40?
1800.
1800. 4200. Okay, so what will be the difference here? 100? Minus 1800. What will be the difference on the right-hand side?
2400.
Divide both sides by 100 and you get 24 amps. So I2 is 24. Now we can get I4. We saw that I4 was equals to this. So where there's I2, we'll now put 24. This will be 48 minus 40. 8 amps. Again, we go back. We made the subject of the formula I3 here. So now we know what I2 is. So we have 4. I2 is 24 minus 90. So this is, what will be the answer here? 96?
Yes.
Giving us 6 amps. So we now have I1, 30 amps. I2, 24 amps. I3, 6 amps. I4, 8 amps. Knowing these, we can now easily get the branch currents that they wanted. So from here, we see that I1 minus I2. So it's 30 minus 24. The branch current here is 6 amps. Next, I4 minus I3. I4 is 8. I3 is 6. We get 2 amps. Next, I4 minus I2. That's 8 minus 24. Giving us minus 16 amps. ID is equals to I3. I3 is 6 amps. IE is equals to I4. We have 8 amps. And there we have it. This is how you work it out. You see, this was a little bit more involving. So when you compare the 10 marks for this example we've just done and the 10 marks for the other one, there is a big difference. I'm guessing one was a test, one is an exam, perhaps.